to do two things today. The first is we're going to review what we've done so far with our vectors. And for that purpose, I'm going to give you an object travels with the position RT given by natural log Ti plus root Tj for t greater than or equal to 1. And if you are listening at home, we hope you get better soon. And we also are going to do a bunch of different problems with checkpoints along the way. So for each question, just pause the tape and answer the question, and then we'll go from there. So the first two things that I want you to do are to find the velocity at time t equals 4, and then find the acceleration at time t equals 4. Go. By the way, feel free to use a calculator to answer any or all of these questions. You definitely will want to for a couple of them. Okay. How are we doing? Almost there? Okay. Evan, go ahead and give us the velocity.
Like all the steps?
Sure. That'd be fine.
Okay. Well, I just took the velocity equals the derivative of t, comma, derivative of
Mm-hmm. And so your velocity vector was?
Well, 1 over t, comma, 1 over 2 for t, and then 4 equals.
And so you get that right there. Good. I noticed that you're using the comma notation, which is perfectly fine. And the acceleration, Smith? Recast this.
Oh, wait, sorry. T to the...
There you go. Okay. Okay. And so the acceleration at 4 is... Yeah. I find when I'm evaluating fractional powers, it's easier to do the denominator first. So t to the 1/2 will be 2. T to the the other way, you end up doing the square root of 64, which is larger numbers of the posterior. Okay, good. All right, next thing. Find the speed as a function of time t, and with that speed, find the distance traveled between times 1 and 4. Go. Catherine, speed.
The square root of 1 over 3 squared plus 1 over 2 square root 3 squared.
Which I'm just going to simplify to 1 over 4t. Distance traveled, John.
going to flat.
Uh-huh.
Speed.
Yep.
Taking
Because,
integral, but I didn't think we wanted to do that.
of course not. Why would I want to do such a yucky integral by hand? Psyching out the question is not a problem-solving technique. Well, sometimes it can, but rarely is it. And when we do this integral by hand, what did you get?
Or is that not-
Excuse me, by calculator, which is not by hand, right?
2.8008.
8008. Let me just double check, because I got a different response, but, I mean, a different answer, but it may be that I did something silly. 1 over x squared plus 1 over 4x. When I integrated that from 1 to 4, let's check and make sure, I got something different. I got 1.7169. Anybody else get that? I have square root 1 over x squared plus 1 over 4x. Now, here's one thing that might make a difference. Did you group your 4x in your denominator? Ah, yeah. So that's actually going to make a difference in the way the calculator interprets it. Because without this, it's going to interpret it correctly as 1 over 4 times x. So the correct answer, I believe, is 1.7169.
What was wrong with first?
So there is a difference between these two.
Oh.
Yep. And you have to be careful to make sure that your denominators are correctly expressed. Okay? All right. Let's see here. Find, same curve. Find dy dx at t equals 4. Charlie, you're on.
So dy dt is 1 over 2.
Okay. No. Just wondering where you're going.
And dx dt is 1 over 2.
Uh-huh.
And then dy dx is dy dt over dx dt.
Mm-hmm.
Which is 1 over 2t over 1 over 2, which is square root of t over 2, and then 4 over 2.
Okay. There's something I like about this solution, and there's something I don't like about this solution. First of all, your math is completely correct. And what I do like about this solution is that you gave us a general answer that could then be used to find dy dx at any time t. And so that's kind of cool. What I don't like about this is that it was remarkably inefficient, given that we could have recycled some work. How?
Oh. Velocity?
Yes, we had already computed the velocity vector right here. And because of that, we knew the value of dy dt at t equals 4. We knew the value of dx dt at t equals 4. 1/4 divided by 1/4, boom, done. You see that? Now, I only say that to say this. Your solution is not a bad solution, but if I were working on a multiple choice test or under time pressure or something, I want to look for opportunities to recycle my work.
So how did we use it with the velocity vector?
Well, what is that velocity vector? Velocity is equal to dx dt I plus dy dt j. That's what you need.
Yeah.
So the components of the velocity vector, the x and y components, are the slope of the line tangent because the velocity vector is always tangent to the curve. Okay, good. Related to dy dx, find the trajectory y of x. And Philip, what do you got? What's your goal? Okay. How are you going to get there? Two words. How's he going to get there? T. That's one word. What about T?
B over
He's possibly going to substitute, but generally speaking, we describe it as he's going to E-word send or get rid of. Eliminate. He needs to eliminate the parameter T. Now, he can do that through substitution, he can do that through elimination. Which one seems preferable? Go ahead.
So I had y equals root t and x equals l to t, and then you do e to the x to the l to t, and then y equals derivative of x.
And there you go. That's our trajectory. Easy peasy. We're eliminating the parameter T. Okay.
I'm sorry.
Yes. Trajectory is y as a function of x. Yep. And so now I could actually sketch this guy right here, and I'm going to get a curve that is going to be something like this, and it's going to be extending like arrows in this direction. Okay. Where are we? Next question, our last question actually. Find the unit tangent t and the unit normal at t equals 4. Go. Mikey, all right. Give us the unit tangent. this can be profitably simplified. Close. I plus j over root 2, actually. So you have root 2 over... Yep, good. You said it right. Very good. Now that you have your unit tangent vector at t equals 4, the unit normal is easy to find. Charlie?
Equals negative I over 2 plus j.
In other words, flip and negate. Now, let's just check because we're not sure which one to negate just yet. So let's take a look at the curve right here. And when we look at the curve, we see that the unit normal should point backwards here. So you have, in fact, done the right one. Pro tip. If you are traversing your curve in a counterclockwise fashion, you're going to end up negating your x component here. And if you're traversing it in a clockwise fashion, you'll end up negating the y component right there. That's some deep magic that's related to the idea of traversing with a positive orientation or a negative orientation. And ultimately, far in the future, that's going to relate to line angles and to G's theorem and stuff. Okay, that's good. You guys have done fairly well with this. A couple of you need to practice. And there it is. We are going to now take all of this stuff and we're going to relate it to the idea of curvature, which is how curvy a curve is. We're going to define curvature, K is for curvature, it's actually cap is for curvature, as the magnitude of the rate of change of the tangent with respect to distance traveled. Now that seems strange, so let me explain it. Let me explain what's going on. Recall that the tangent vector is a unit vector. It gives us direction of travel only. So if I'm going along a curve and I compare the road at this point, T1, to the road at this point, T2, then what I can see is that as I move along the curve at T1, like so, my tangent vector is hardly going to change at all. My tangent is going to have a very slow rate of change with respect to a small distance traveled. And the reason that I use s and not t is that it might be that my speed would be variable along the curve, and the curvature is really a property of the curve itself, and not the speed that I'm traveling along. So I'm using the distance traveled along the curve as my metric. Meanwhile, if you contrast that to what's going on with T2, my tangent vector is going crazy over here. Look at how much it changes by as I move a little distance along the curve. So we would say that this is a curve with high curvature, K, and this is a curve with low curvature, K, and we can measure that with, as the size of dTds. Yes.
Subject hardly changes.
What's that? Hardly. Changes little. I'll rewrite that. Here, the tangent t changes greatly. With Okay, well that's fine, but now the question is how do we actually compute this? And it's going to turn out to be really elegant and nice. And so we're going to develop this in a couple of steps. The first thing that I want to observe is that the rate at which t changes with respect to s is related to some other quantities that we talked about. Recall that, first of all, our unit tangent t is the same as v over the speed, over the magnitude of v. And the unit normal was equal to the rate at which the tangent changes with respect to time over that magnitude. And since these quantities here kind of look like each other, I figure I might want to do some algebra with them. So the first thing that we want to do is to observe that I can rewrite the velocity vector as speed times tangent. This is just a way of saying magnitude times the direction vector. And likewise, the rate of change of the tangent with respect to time is the magnitude times the direction. So that's just a little bit of algebra right there that we're going to use in just a moment. And then the second thing that I'm going to notice is that I can relate these quantities here and here using the chain rule. So that dt dt is the same as dt ds times ds dt, just like that. And this, of course, is my curvature. What is ds dt? ds dt is the rate at which the distance is changing with respect to time. Oh, that's the speed. Is that really true? Yes, actually it is, because remember that s is going to be the integral from 0 to t of speed dt. And so ds dt, using the first fundamental theorem, is automatically the speed. Ta-da. So we can immediately say that this quantity, the absolute value of t dt, is equal to the curvature times the speed. Interesting. Okay. Now, here comes the magic. Remember that when we took a curve, let me just take our curve here and copy it. Remember that when we took a curve, let's take our curve on the next page, so we'll have plenty of room to work. Okay. We, at any point, could draw the velocity vector, and then we could compute the acceleration, like so. And then we created the idea of the tangent vector and the normal vector so that we could have a reference frame in the direction of travel. So t is going to be like I, or the vector in the direction of the x-axis, for the direction of travel, and n is going to be like j, it's going to be like the y-axis, perpendicular to the direction of travel. Okay? And so we can take any vector, such as the acceleration vector, and resolve it into the components a dot tt plus a dot n times n, just like this. And we call this the decomposition of the acceleration into tangent and normal components. What I'd like to do is to explore these tangent and normal components and their meaning. And I'd like to do it like this. I'm going to start by writing the velocity vector from the previous page as speed times tangent. Keep in mind that this is a scalar quantity here times a vector quantity right here. So we're taking the unit tangent vector and we are stretching it by the speed to get our velocity vector just like that. Okay? Now, we're going to get the acceleration by taking the derivative of this guy right here. Because the acceleration is dv dt, which is going to be equal to product rule. Speed times dt dt plus t times d speed dt. Note that these are not dot products. This is a legitimate scalar, speed times a vector, plus vector times scalar quantity. But wait, because, as we saw on the previous page, dt is the magnitude of dt times the normal vector. So that what we have accidentally done here is to resolve the acceleration vector one more time into normal and tangent components. These guys here have to be the same as these guys right here, because our decomposition is unique. So remember that the normal vector is equal to this quantity by definition. So if I multiply those sides, yep, and write a little bit larger, then I get the result. Okay? Good. But then also remember from the previous page that we established that dt is the same as curvature to dt. So that when the dust settles, if I take these terms and write them in order, then I get dt times the tangent plus v squared k times the normal. And this is for any curve. Now let's examine what each one of these means. We can think of this component, the tangential component, as the projection of A onto T, because it is the component A dot T. And look at what that projection of A onto T, or the tangential acceleration, gives us. It gives us the rate at which the speed is changing. The tangential acceleration is telling us how quickly our object is speeding up or slowing down. So that if I get A dot T is a positive quantity, my object is speeding up. And if I get A dot T as a negative quantity, my object is slowing down. Aha! That's the generalization of the rule that we had for motional line. Remember our sign rule? If acceleration and velocity have the same sign, then the object is speeding up, and if they have opposite signs, it's slowing down. This is that rule generalized. If acceleration is in the same direction as the tangent vector, then it will have an angle between 0 and 90 with the tangent vector, and its cosine will be positive, and we will get a positive rate of change of speed. And if the acceleration vector, so here's an example of speeding up. If, on the other hand, the acceleration vector is pointing backwards with respect to the tangent vector, then my angle here will be greater than 90 degrees, and I will get a negative cosine for my dot product, and I will get therefore a negative rate of change of speed. My object will be slowing down. So that's what this guy tells us here. Now what about the normal component? Well, the normal component is going to indirectly tell me my curvature. But actually, we can say a whole lot more than that. And to say a whole lot more than that, I want to consider the concept of a tangent circle. Yes?
Sorry, but I was lost in the K part.
No problem. Why is this?
No, the before that?
Here, there. Okay? Right, so this is what we did on the previous page. We took this quantity right here, dt, and we used chain rule to rewrite it as dTds times dsdt. And dTds is, by definition, the curvature k. dsdt is, by fundamental theorem, the same as the speed. Okay? And then just substitute and you're good. Better?
Why is that,
Why is that equal to A dot n? Ah, yes. So notice what I've got. I've got acceleration is something times t plus something times n. In other words, it is the decomposition into the tangential and normal components. But that decomposition, by definition, is equal to A dot t in the t direction and A dot n in the u direction, because each of those are normal vectors. Better? Good. Great questions. All right. So let's come back to this. What we'd like to do is to get some insight by considering the idea of a tangent circle. And the idea of a tangent circle is that I'm going to place a circle at any point, let's say this point right here, so that not only is the speed of the circle the same, or the tangent to the circle the same as the tangent to the curve, but the curvature of the circle is the same as the curvature of the curve as well. And that's a little tricky to do visually, but I think this pretty much does it right here. You can see that the curve is hugging the circle at just the right curvature at this point. Okay? So the question we have now is, what is the curvature of the circle? And let's do that. And since we're short on time, we'll do it kind of quickly. Let's start with our standard circle in the standard form, r cosine omega t I plus r sine omega t j. And we'll compute the unit tangent and unit normal vectors. V of t is going to be equal to negative r omega sine omega t I plus r omega cosine omega t j. Taking derivative there. And the magic of our circle is that when I find the speed, it is going to be equal to simply r times omega. So that the unit tangent is equal to negative sine omega t I plus cosine omega t j. And what we're looking for is the curvature of our circle. And so we're going to write that as dt dt divided by ds dt, just like that. Again, using chain rule here. And we can compute each one of these pretty easily, because the derivative of the tangent is going to be negative omega cosine omega t I, and the derivative minus omega sine omega t j. And the speed we already created up here, that is the ds dt is the same as the velocity, which is r omega. And once again, with the magic of the unit vector cosine I sine j, we get that the magnitude of dt dt is simply omega. And when the dust settles, we find that our curvature is simply the reciprocal of the radius. And that's a really nice, elegant result. It means that for any given circle, I can find the curvature immediately as the reciprocal of the radius. Well, taking this result now back to the previous page, I can substitute here and find the result that you probably remember from physics, and that is that the normal component of the acceleration is equal to the square of the speed divided by the radius of curvature, v squared over r. In physics, we call that the centripetal acceleration. Do you remember that from way back when? Yeah, from way back, like a month ago or something. what we have found then is that the components of the acceleration in the tangent and normal directions have useful physical meaning for us. The tangential acceleration tells me how quickly I'm speeding up or slowing down. The normal acceleration tells me indirectly the curvature of the curve that we're traveling on. Yes. Sure can. Yes.
Sort of the bottom,
Projection. Yeah, so this is kind of the question that you had yesterday. So let's take a moment to look at that. If I have a vector here and I want to project it in the direction of B, and what I'm trying to do is to find how much of A is in the direction of B. So if I do it geometrically, I would say that this side AB is equal to the sides of A times the cosine of the angle between. But the cosine of the angle between is equal to A dot B divided by size A size B, so that I end up with a fairly elegant result. AB is equal to A dot B over B. If B is a unit vector, size B is 1. So if I had, for example, AT, then I'm going to simply get A dot T. Yep. Now think about your I and J. If I have a vector like 3i plus 4j, and I dot that with I get 3, which is the component in each direction.